telling us about how simulating balls and springs captures the power of quantum computing. So welcome, Robin.
All right. Thanks, Sandy. And thanks to all the organizers for inviting me. Yeah, thanks so much. I've been to the Simons Institute many times, and I've loved every single visit, so please keep inviting me. All right. So I'm going to talk about how simulating balls and springs captures the power of quantum computing. And a more traditional title slide would be, this is the actual title of our paper, an exponential quantum speedup in simulating coupled classical oscillators. I'll explain what all that means. And this is joint work with Ryan and Rolando at Google, Dominic at Macquarie, and Nathan at University of Toronto. And that's where you can find it on the archive. Okay, so one slide summary of what this talk is about. We define a new computational problem, and this new computational problem is related to simulating the time evolution of a classical system of a bunch of balls connected by springs. And what we show is that this problem can be solved by a quantum computer efficiently. So the problem is in DQP. And the upshot of this result is that, well, maybe we can find new applications for quantum computers. Maybe we can find classical systems in the wild that people want to simulate, and then you map it to our problem, and then you use our algorithm. So that would be the upshot of this result. On the other hand, we also show that the problem is BQP complete. One interesting thing about this is that it's a purely classical problem, as I'll describe to you. But the other upshot of proving something BQP complete means you can design new quantum algorithms through the classical system. So you could recover known quantum algorithms by just analyzing systems of balls and springs in this case. And I'll give you an example of that as well in this talk. All right, so this is going to be an outline of this talk. So I'll first explain what this problem is, the one that I've been talking about that is BQP complete. And then to discuss how you solve this problem, I'm going to do a review of Newtonian mechanics. So I want to mention two things about this. First, this part might be really boring to the physicists in the audience because, like, you probably know this, and this is really basic. So please feel free to zone out or go on your phone, look on Reddit. And secondly, for the same physicists in the audience, if you catch me making mistakes, please point this out because I'm not an expert in Newtonian mechanics. So feel free to interrupt. I mean, we've already had a lot of good discussion at this conference, but feel free to say, raise your hand or speak up if I make a mistake, explain any of the physics stuff in this talk. And once I describe the problem, and once I describe how you solve this problem classically, I'll tell you our quantum algorithm, and I'll give you some evidence for why this problem is hard. That hopefully will be interesting. Okay, so let's start with the first part. What's this problem about? So this problem follows this general class of problems that you've probably seen a ton of if you took high school physics, which is you're given the description of a system and how it evolves in time, and you're told what the system looks like right now. And then you're asked to predict what the system will look like after time t. So like in high school physics, you have these problems like there's a ball and it's moving with some speed and it's acting under the force of gravity, and you've got to predict its, where it's going to be, its position and velocity at time t, or maybe there's an inclined plane or whatever. This is like a classic, physics problem, just the time evolution question. And so, for example, if we talk about classical physics or like Newtonian mechanics, this problem would look like this. I'll tell you the state of the system right now at time t equal to 0. This will be the positions and velocities of all the particles involved. And I'll tell you how the system evolves with time. And classically, this would be Newton's laws. And for me to tell you Newton's laws, which is like F equals ma, I need to tell you, well, both sides of the equation, which means I'll tell you all the forces acting on all the particles, and I have to tell you the mass of all the particles. And to make this a computational problem, what will be your inputs and outputs? I'll give you these forces, masses, the initial positions and velocities, and this time parameter t. And you have to output the position and velocity at time t. So this is how I'll make it a computational problem. Okay, so this is just a general framework of how these problems look like. Now let's specialize to balls and springs, the advertised physical system that we're going to talk about. Okay, so what's going on here? So there's going to be n balls, and any pair of them can be connected by a spring, but like just for this example, I'm going to put them all on a line and just connect the nearest neighbors. And I'm also going to allow any of the balls to be connected to a wall by a spring. So in this example, I've just done it on the two balls at the end of this picture. So here n equals 8, and I have 10 springs. Okay, and so I want to analyze the dynamics of this system. So I want to know what happens if all these springs start like this, and like they start at these positions and all the velocities are 0, maybe it just stays like this. But if I perturb one of them, I want to know like how this system evolves in time. And as I said before, what do we need to know to understand the time evolution of this classical system? You need to understand the masses of all of these balls, and you need to understand the force acting on each ball. And for the force exerted by a spring, there's a simple formula. It's called Hooke's law, and it says that the force that a spring exerts on a ball is minus kappa times delta x. So kappa is the strength of the spring. So if kappa is 0, that means there's no spring. Kappa being large means the spring is really strong. And delta x is the amount by which the spring is compressed or elongated. And there's a minus sign to show that, like, if you compress the spring, the force is outwards. So it's an opposite of the direction of delta x. Okay, good. So this is all I'm going to say about how, like, the physics of the system right now. So I'll come back to it later in my Newtonian mechanics review and explain how you actually solve this computational problem. But right now, I just want to give you this basic idea that once you know this, in principle, you can answer any question about this. Once you know the force equation and you know the masses, that's all you really need to know. Oh, good. Are there any questions at this point? Sorry? That's right. You also need F equals ma. Yes.
So your springs will always be harmonic. So Hooke's law is, when you say spring, you mean Hooke's law.
Right. When I say spring, I mean something that follows this equation. That's right.
Good.
Yeah. Any more questions?
What are the parameters that you can include in this differential model?
I'll tell you on the next slide, but basically the masses and the strengths of each spring. And of course, the initial position and velocities are also in your control. But yeah, okay, let me formulate a computational problem. So if this is all I told you, like, the most natural computational problem you would come up with is this one on this slide, which is there's 4 inputs. The first one is all the masses. So I'm going to call them M1 through Mn. Then there's spring constants. So how many of them are there? I allow each pair of balls to be connected by a spring. So that's n choose 2 spring constants. And then I allow each of the balls to also be connected to a wall optionally. And any of these spring constants can be 0. So, like, you don't have to have springs everywhere, but, you know, allowing for this possibility. So there's n choose 2 plus n numbers kappa. I'm going to arrange them in a matrix. So kappa ij is the spring that connects ball I and ball j, and kappa ij is the same as kappa j. It's the same string. And I'm going to say kappa ii is the value of the spring constant connecting the ball to the wall. Okay, so that's a description of, like, essentially the Newton's law part, the mass and forces. Then the initial positions and velocities. This I'm going to denote as, so I'm going to use x for my position, then x1 to xn for the n masses, and the argument is the time. So at time 0, I want to know all the positions. And for velocity, I'm going to use this notation of putting a dot to represent time derivative. This is very common in physics. So xi dot means the velocity of the ith particle. Again, at time 0. So these are the initial positions and velocities.
Numbers or vectors?
The xi's are numbers. That's right. So
one-dimensional.
I didn't say this earlier, but yes, everything's one-dimensional in this talk. But this is.
Is there a reason for that, or just what you think so?
It's easier that way.
That's
But it's not. It's yeah. It's not that it's more. Yeah, and also it's essentially without loss of generality, which I'll maybe talk about a little later on. Like, what will happen is, if you want to talk about, like, 3-dimensional systems, you'll essentially use 3 coordinates for each coordinate of the original 3D object, and it'll work out. But let me focus on the 1D case for now, and I'll come to it.
But if it's 1D, how do you connect to a wall? I mean,
You know, like, I mean, it's 1D only in the sense that I'm using one position variable. Like, it's just, it has to satisfy those equations, right? That are down, which is like.
so I should think of this as if it's connected to.
Yeah, maybe you can actually build it in 1 dimension. It's just I'm using one real coordinate for every particle. So this, I mean, I'll talk about this later, but, like, this system of equations doesn't just capture balls and springs, but it captures, like, a whole wide variety of phenomena in physics where, like, these things may not actually be balls or springs. They might be, yeah, other things. And these equations could come up where everything's coupled with everything. But yeah, if you're just thinking of a simple system of balls and springs, it's a bit unnatural to have springs going through other balls. but the equations will make sense as written.
But you do allow the balls to go through each other.
Yes, I allow the balls to go through each other, springs to go through each other, right? Balls to go through walls. Which, yeah, so, it's all good.
Consider the physics explanation.
Oh, yeah, for the that's right. Yeah, when I was making the slides, I was trying to think, like, what audience am I pitching it to, and I was like, let me just pitch it to the computer scientists in the room. It'll be, you know, the physics folks might zone out of the physics part of the talk. Anyway, they'll be like, we know how this works. Like, explain this to us. But I'll tell you the equations of motion, which is probably what the physics people care about. And once you see those, you'll be like, oh, this is just classic coupled harmonic oscillators. I don't need to care about all of your stories so far. So most of the story is just for the computer scientists who don't know or saw this so many years ago and forgot this is in high school. Yeah, question?
So which wall is the ball is connected to? Because it depends on affects which direction it's pulled in.
Right, that's a good question. When I show you the equation of motion, it'll make more sense. Yeah, what the wall term corresponds to. It just corresponds to a term in the equation of motion, which is like minus kappa I xi.
So you're fixing a canonical wall for all the walls then.
That's right, except all of my position coordinates are with respect to the rest positions. So it's not like the walls are all. So yeah, maybe I should say this earlier. It doesn't really matter. Right now, it'll make. I mean, it'll matter once I set up the equation of motion. But what I'll want to do is I'll want to have each of the x coordinates relative to where they start from. So in this position, for example, I want all of the x coordinates to be 0. Like all the velocities are 0 at this point. I'll also have all the x coordinates 0, and this will correspond to the vector of position velocities being the all zeros vector. And so the walls will be with respect to this canonical position.
Suggestion, Robin, for next
Yes.
time you're
Yeah.
having this talk is this: make it inductor and capacitor circuits, and you'll get rid of a lot of these comments. Entirely equivalent.
That's right.
Shut up the physicists.
Right.
Physical layout.
Yeah, that's fair. Oh, sorry.
Yeah, wires. It's less of the problem.
That's right. Or yeah. Or maybe have one slide for physicists, so I just give you the equations of motion, and everyone's like, that makes sense. But anyway, for now, let's just think of balls that can move through balls. Springs can move through springs. That's okay. Okay, so this would be one way you would try to formalize a computational problem. I give you all of this, the equations of motion. I tell you the initial positions, velocities. I tell you time t, and you have to output the final positions and velocities. Well, that's a totally reasonable way of formalizing this problem. Except this problem is, I mean, you can't have a quantum speedup for this problem because, well, so what's going on? Firstly, you can solve this problem classically in time polynomial in n, the number of masses. And the output size is also n. So like any algorithm, whether classical or quantum, would have to write down an output of size n. There's not really going to be an exponential speedup. So I want an exponential speedup. So this is not the version of the problem that I'm going to be talking about, but this would be just the most obvious way to write down a computational problem. So what I want to do is come up with a different, like a version of this problem, which is still essentially talking about the same system, but I want to encode the input succinctly. And that's going to open up the possibility of an exponential speedup. So how do I do that? I want to specify all of these 4 inputs succinctly, and also want the output to be small, because right now it's an output of size n. That's no good, because if you have an output of size n, you need n time to write it down. So I'm going to change the way I represent all of these things. So let's start talking about how I'm going to do this. Okay, so as I said, we want succinct inputs, and what I mean is, if capital N is 2 to the little n, I want inputs that are of size polynomial in little n, or in terms of the original capital N, it's polylog capital N. Okay, so how do we deal with the masses? So if you remember from the previous slide, there's n masses, right? And I want to describe n things to you, but I want to only use like polylog n, an input of polylog n size. So one thing you can do is you can just assume that you're given a circuit that describes the masses to you. So I'll give you a polynomial size circuit that accepts as input the name of a mass, the label of a mass. This is a number between 1 and capital N. It does some polynomial time computation and spits out the mass, mi. So what this means is, of course, that a polynomial size circuit cannot encode arbitrary lists of n numbers. So this is saying that the masses have a lot of structure, that there's some formula that tells you what mi is from I. So for example, the ith mass could be I squared. That would be an acceptable example where you would have a polynomial size circuit. Or all the masses are the same. They're all mass 1. So things like this. So we're going to restrict our focus to special cases of this problem where I can actually encode the input succinctly. And the choice I'm going to make here is that the masses are represented by a polynomial size circuit, which takes as input a label and outputs mi. Okay. Does this make sense to everyone? Because I'm going to do more of this, this kind of trick. Okay. So that was masses. That was a vector of length n. The second thing is this set of spring constants. So this is like this is a matrix. This is an n by n matrix. So what I'm going to do is I'm going to assume 2 things. Firstly, this matrix I'm going to assume is sparse, and what that means is, although it could have up to 2 to the n entries in any row or column, I'm going to assume that it only has polynomial in any entries in any row or column. And the second thing is, again, same as this. I'm going to assume there's a circuit that describes this for me. So formally, this matrix, this kappa matrix, it's sparse, has poly n non-zero entries. And again, there's some circuit which takes as input I and outputs all of the non-zero entries in row I. So there's only polynomially many of them, so that's not a problem. Sorry?
Each mass only couples to a polynomial number of elements.
That is right, yes. So in this version of the succinct problem, I'm now going to assume that this coupling is sparse. So every mass can only be coupled to polynomially many other masses. And again, this is represented by a polynomial size circuit that takes in the name of a mass and tells you all the masses it's connected to and all the spring constants of the springs between those pairs of masses. And this is a list of polynomial sizes, so that's not a problem. Any more questions about it? Okay, good. So these are two of the four inputs that I've shown you how to encode what we're going to assume about their succinct encodings. The third thing was the list of initial positions and velocities. And so here what I'm going to do is I'm just going to assume these vectors are sparse. So that means although they're vectors of size 2 to the n, I'm just going to assume there's only poly and non-zero entries. And you just tell me what all these entries are, and the others are 0. So again, that's a polynomial sized input. That's good. The fourth thing was time. It's just a number, so it's not a big deal. But I didn't say this earlier, but all of the numbers appearing so far, I'm also going to require them to be polynomial sized. So I'm going to recap all of these requirements, but I'm just telling you now that this is also another constraint I'm going to put on the problem. So you can't have like a spring constant that's of size 2 to the n, or a mass that's of size 2. Like, I'm not going to allow that either. So this completes the input. So what's left is the output, right? So the output was, again, the position and velocity of every particle or every ball at time t. So we can't do the same trick that we did for the inputs there. Yeah.
Is there a reason why, say, for 3, it needs to be sparse versus just efficiently computable?
For 3. No, yeah, efficiently computable is not okay. There's something a little more general than sparse that's going to be okay, and it's going to relate to what kind of quantum states can you prepare on a quantum computer in polynomial time. And sparse states is one example, so that's why I'm going to use that example throughout. But more generally, it'll relate to like what quantum states have efficient quantum circuits. But certainly, just being able to compute entries is not sufficient.
So you say that these most poly n, or the description of these at most poly n?
No, T itself is at most poly n.
So, okay. Yeah.
And I'll recap all these constraints on the next slide. So you don't have to load them in memory. I'll show you everything again, but I'm just walking through each of the inputs and outputs one by one, telling you how I'm going to make them succinct. Any more questions?
Sorry, but at this level, you've basically encoded a local quantum Hamiltonian, which is calling to things as springs. So I don't see why you have to invoke balls and springs at all, because it's a 2n by 2n matrix at this point. In Hilbert space, a local Hamiltonian is also a sparse matrix that's 2n by 2n. So
That's right.
I'm not really seeing that.
I mean, this is very analogous to like the class of Hamiltonians that we usually focus on, right? So we talk about like simulating like quantum systems on a quantum computer, but we don't actually mean we can simulate any old Hamiltonian. We usually restrict our focus specifically to sparse Hamiltonians, which is exactly of this form. So I'm saying we're doing the same thing, but instead of for Hamiltonians, for this matrix of spring constants. Yeah. But the dynamics are different, right? It's not Hamiltonian dynamics. It's Newton's laws.
The way you'd solve the string problem is by diagonalizing the same matrix. So it seems to me that the red herring to talk about balls and springs when it's really just diagonalizing a large matrix.
That's true. Classically, if you were to solve Hamiltonian simulation or the solve of string problem, you would diagonalize this exponentially large matrix. But the equations of motions are different. So it's not like I'm literally solving the same problem, right?
Well, the other position.
I will end up with a differential equation. That's right, but it will at least not obviously be the Schrodinger equation. But
How do you solve a differential equation? You make a first order,
and that's right. And
then exponentiating it. So
that's right. Eventually, this is why, and that's the reason why this system will like capture the power of quantum computing as a phrase, because it will be BQB complete, because you are able to both simulate it by mapping it to a quantum Hamiltonian and vice versa, map a quantum Hamiltonian back to a system of balls and springs. So yeah, you guys are already seeing where this is going, but yeah, any questions about how we're encoding stuff? Just so everybody's on the same page, and especially those of you who are seeing this for the first time, like how we encode exponentially large objects with polynomial sized inputs. Right, so, okay. And so I haven't finished because I've only told you how the inputs are encoded. The output from the previous slide was also some exponentially large vector, right? You have to tell me all the positions and velocities. And unlike what we did for the input vector, where we said, well, let's just assume it's sparse, you can't just assume the output is sparse because the output is not in your control, right? It's just some vector. And there's several things you can do here for the output. I'm just going to ask for something simple. I'm only going to ask for the velocity of the first ball as the output. So that's going to be my new output. Instead of telling me all of the positions and velocities, I'm just going to say, tell me the velocity of the first ball up to this additive error inverse polynomial. So let me put all of this together and give you like a formal problem definition. So I'm calling it a simplified decision problem because, well, it's a decision problem. Like you just have to output yes or no, the way I formulated here. And it's simplified because the actual problem we solve is more general, but it's OK for you to focus on this for the rest of the talk. This problem will be BQP complete, and it'll have all the properties I talked about. And yeah, this will be, we can design new quantum algorithms using this version of the problem and so on. So we don't necessarily need to talk about this general problem, but I will get to it later on. But if you're seeing this for the first time, it's a little overwhelming to see the general version of this problem. So that's why I just want to focus on balls and springs. Okay, so this is a summary of the stuff I talked about in the last 2 slides or so.
Your third criterion that so only polynomial are non-zero, so the rest of the balls are just sitting.
Oh, right. It's good to, yeah. So I'm going to measure everyone's position relative to the rest position.
Okay, got it.
So for example, in this line case, like x equal to 0 for all of them would correspond to them being equal to space or whatever. Yeah. So yeah, all of them being 0 don't mean they're all on top of each other.
As a follow-up on an earlier question, what you're doing here is really to generate a random-ish, like permission sparse matrix, and talk about the second-order differential equation associated with this permission matrix. I mean, that dynamics is BQP, right?
Right. That is also, yeah.
So maybe a more basic question is that clear? The first-order equation corresponding to the same permission matrix is BQP, which is you consider the Schrodinger version of it, and is that clear? It's a well-known result that's BQP. Time-independent Hamiltonian simulation with this particular input matrix.
Oh, I see. You're saying whether is time-independent Hamiltonian simulation with
This particular matrix.
this kind of matrix. So you mean like this matrix differs from an arbitrary Hamiltonian because, like, firstly, all the numbers are real, but in fact they're all positive.
So this is a classical second-order Newtonian dynamics. So you can actually write down for example, you can double the, if you use the position and velocity as the phase space, just an indexes. You can write down at the
I'm asking a little bit different question, which is the difficulty here is because the matrix size is very large.
I see.
Right? And so the way to argue about BQP is you start from this matrix, you consider this a second-order differential equation, and say that's what BQP can be. Great. Right? But I'm asking whether there is to this community, the quantum computing community, whether the more basic question has been answered. That is, I partial t psi equals to this matrix times psi is BQP.
Right. So I guess maybe what you're asking is, yeah, is Hamiltonian simulation time-independent Hamiltonian simulation complete if I restrict the Hamiltonian to be so in this version they're all positive numbers in the Hamiltonian.
We don't know.
That's
Quantum walks. I mean, Charlie Law paper showing that quantum walks are universal basically uses a positive force.
oh, yeah. Okay. Yes. So we do know the answer.
Okay. So then, if that is already known, because I didn't know whether it was known, what's really the new thing compared to that?
So yeah, let me tell you after I describe the differential equations and so on, because yeah, maybe most people here don't know what I'm talking about. Definitely don't know what you're talking about when you talk about a second-order differential equation described by this Hamiltonian. So yeah, let me talk about those and I'll come back to this. Okay, so this is our problem. No more questions. Good. And what's the main result? The main result is that this problem is in BQP. And in fact, there's also a more general problem I'll talk about later that's also in BQP. But so, I took this problem that at its outset was pretty interesting. It was about simulating a system of balls and springs and whatever. But then I introduced a whole ton of constraints, right? So you might be worried that now I made the problem too simple, right? So is this problem too easy now? Like, is it that I put so many constraints on the problem that this problem is now easy to solve classically. So that's not clear right now, right? Because yeah, all I'm saying is that this problem is solvable on a quantum computer. So the second thing shows that the problem is also BQP hard, and hence BQP complete. And in fact, it remains BQP hard even if we make further special assumptions, like we can take all the masses to be 1, all the spring constants are bounded between like 0 and 4, whatever. And the sparsity is a constant. And in fact, the initial state is very simple as well. All the positions are 0, so they start at the rest positions. And all the velocities are essentially 0 except like 2 of the masses have some velocity. So even in this very special situation, the problem remains BQP hard. And another evidence that we give for the problem being hard is that if we think of this problem in the world of query complexity, so which is where you now have some black box that knows the spring constants. So the same setup as now, like there's this matrix of spring constants, it's sparse, but it's not written down anywhere. You're not given the circuit, but you're given black box access to it. And now the question is, how many queries you have to make this black box to solve this problem? So what we can show is that any classical algorithm, or deterministic or randomized, would need 2 to the omega n queries to solve this problem, whereas our algorithm solves it in polynomial many queries. So if you want, you can view this as a query complexity separation. And I'll tell you more about this result because it's kind of nice. The way we prove this is we show how you can solve the glued trees problem, which is a famous query complexity problem with an exponential separation between classical and quantum algorithms. We'll show how to solve this glued trees problem by mapping it to a system of balls and springs in kind of the obvious way. Okay. So that's a statement of my results. There's no questions about this. Maybe I'll come back a little bit to this question of why are we focused on balls and springs, and this also. This was related to Toby's suggestion that like maybe I should talk about like electrical circuits with capacitors and inductors, and that would be an easier explanation for physicists. Yeah, I don't know how familiar computer scientists are with capacitors and inductors. I don't know if that's an easier model to start with, but anyway, I'll think about it. But the point is that the same equations of motion that you write down for the balls and springs, essentially the same ones also appear when you do a whole bunch of other things like electrical circuits and motion coupled pendulums. Analyzing vibrations of molecules. So it comes up all over the place. And yeah.
I have no problem with your mathematical setup, but I have a little bit problem with all this physical implications. And the reason is, if you look at for example, the picture you drew before, really for like a lot of balls connected by springs, and it's essentially a phonon system. And I mean, yes, it can be very, very large, but the dispersion relation is smooth. So there's a lot of redundant degrees of freedom. It's not like you have an exponentially large number of things. It must be exponentially hard, right? I mean, in that case, you specifically know that it's not hard. So you really need, I think, to really show that it is very, very hard, you need to make all this coupling to be kind of really weird. Right? It is not like a naturally mapped to any of these kind of physical setups.
Right. You're saying the hardness of the problem.
Exponentially large number of degrees of freedom and exponentially hard.
You're saying the hardness of the problem will not. It relies on the fact that we can tune all of these masses and spring constants. Like if they were all the same or something, then it wouldn't. That's true. I mean, I need something
Not just all the same, but many.
Or something very straightforward, like some very easy function. That's true. I need some degrees of freedom in the input to have a computational problem, right? Like to prove asymptotic statements about complexity. Like if everything was straight, like if all of them were a known relationship for all the masses and stuff, like where would I encode the difficulty of the computational problem, right? So this is the choice we make, that it's actually hiding in the spring constants, because as I said, like in all of the hardness examples, the masses can all be 1, 2. So it's really the fact that all the spring constants are tunable where all the difficulty is lying. You can even assume the masses are easy.
You said you could, it's BQP, you can reduce the factor into it. Is it clear that wouldn't give you some nice regular spring constants where, it's just a regular pattern?
No,
That wouldn't be.
No, it'll give you something pretty horrible. Each spring constant will be related to like some gate amplitude in your circuit. So, it'll be pretty bad.
Would you think that if it was some regular pattern, it would be easier? So, for example, if there were only n different spring constants and they were according to some gates, a regular pattern.
Then would it be even easier? Like maybe it could be solved in BQP, like a classical. Yeah. I don't have a sense for what that would be. Yeah, so certainly the BQP hardness proofs will require, we need a lot of tunable parameters to embed arbitrary circuits into it. So once that's gone, maybe it becomes easier.
Sorry, polynomial mainly, right? Polynomial.
Yes.
You know that for quantum circuits, you only need a few amplitudes and gates.
Right,
to
so
make everything universal, right? Just
that's right. So
something tough on the line. So you only have a few values of the strings that new, but maybe the pattern is not very.
that's true. I'll only use maybe 4 different types of strings or something with string constant 0, 1 over root 2, 1 and root 2 or something. But the pattern will correspond to the gates in the quantum circuit that you did the reduction from. So if that quantum circuit is somewhat regular, maybe it'll lead to that regular. I think I'm not sure. I have to step to the reduction to see exactly what happens if you start from a nice quantum circuit, whatever that means, like maybe some kind of regular pattern gates that maps to a nice pattern. String constant.
So, just so I understand, I believe that your custom matrix is stochastic, right? All of its off-diagonal entries there share the same size, and then it's the dynamics itself that gives you the BQP hardness. Is that based on the relationship blocks, or?
I'll get to that. I mean, I haven't even described the actual differential equation that we're solving. Those of you who've seen this stuff before know exactly what I'm talking about, but for many of you, let me get to the point, right? Explain what equation is being solved and how it gets mapped to Hamiltonian simulation, and then you'll see what kind of Hamiltonian comes about.
I ask one more question about the sort of physical mapping.
Yeah.
If we start with the geometrically local quantum circuit, do we end up with geometric locality or any kind of structure in the balls and springs?
Maybe, but not no, I think what will happen, geometric locality for your quantum circuit will get translated to something like you only connect masses, balls whose labels are close by in Hamming distance. So it'll correspond to something weird because you're not going to embed the Hamming cube into any local space. So yeah, it corresponds to something weird. If you give me log n dimensions or something or whatever to embed the Hamming cube into space, then maybe it'll be local.
Well, I was going to try and let you carry on, but since there are comments about this, in Hamilton, when we're trying to construct QMA hard or BQP complete Hamiltonians, what we learned is if we want something uniform in space or translation invariant, or the best thing to do is to reduce from Turing machines rather than from gate circuit model. If you want something uniform here, you might find you get sort of uniformity in spatial translation variance for free, kind of by doing a reduction from that. And I bet your techniques just go through for that as for the circuit model.
Right, so you reduce from quantum Turing machines.
Yeah.
Yeah. Yeah, that might work. Yeah. Okay, so for those of you physicists, you probably know why I'm focusing on this system because coupled harmonic oscillators come up everywhere. But just for people who are seeing this for the first time, it's not just that we specifically care about balls and springs, but the same equations of motions come up everywhere. And there's a deeper fundamental reason. It's not like kind of a coincidence. It's like, oh, look, there's like 17 different systems described by the same coupled harmonic oscillator equations. But it turns out because of this thing, if you analyze a physical system at stable equilibrium under a certain kind of physical system, which has a name, which is the physical systems that have where the force is called a conservative force. So that means the force arises from a potential. So the force is the gradient of potential energy. So if you have a system like this and it's in stable equilibrium, so that means everything at rest and velocity 0 will just tend to stay there. So if you poke something, it wants to come back, which kind of reminds you of a spring. Like if you poke a spring, a ball connect a spring, it tries to come back. So it's a general phenomenon. If you have a system in stable equilibrium and you poke it a little bit, or you poke everything in the system a little bit, it tries. If it's stable, this means it tries to come back, and that means if you write down the equations of motion to some approximation, so that's why I'm saying perturb. So perturbatively, if you write down equations of motion, you will basically get the same equations of motion. So this is why these equations come up over and over again, and they're called coupled harmonic oscillators. So if you've seen this come up, it's not a coincidence. There's a deeper reason, and this is why it's interesting. But anyway, if you don't care about the motivation, it doesn't matter. You can just focus on the system of balls and springs. Right. So let me. Okay. So let's do a quick Newtonian mechanics review, or how do you set this problem up as formal computational problem. Like, what are these differential equations that several questions alluded to? All right, so let's just start with one ball and one spring. So it's going to be the easiest case to handle. Yeah.
Talk about equilibrium or stable that as extra condition. That is, the matrix you generate should be positive and down. Is that obvious how to do it?
So the way I set it up with balls and springs, that when I write down the differential equation, that matrix will be PSD, just by construction.
But no, I mean that's a motivation. But the actual setup is you have a polynomial sized circuit that give you I that spells out J and kappa ij. Is that obvious how to construct
Well, in the spring mass system, all I need is the spring constant should be positive. Like I don't need to enforce anything else. The matrix that appears in the differential equation is not the same as the spring constant matrix. It's something like a graph Laplacian. Like it will be positive separation by construction.
Right.
So that's not something I'm going to enforce. Yeah. So the problem as stated was the formal problem. There's no extra stuff to be stated. Good. So okay, let's do a quick review of Newtonian mechanics for those of you who haven't seen this. And let's start with one ball, one spring. So this is what it looks like. And the first thing you might observe is that my balls have now changed to squares, blocks, but it's all the same because they're point particles, they're point masses, so it doesn't matter. So okay, so there's one mass. I'm going to call it M. There's one spring. I'm going to call it kappa. And this is the situation in which like you can just leave it be and the system won't do anything. So this is its rest position. And I'm going to call that x equal to 0. So for all the masses, I'm going to talk about the position coordinate relative to their rest position. And this is what it looks like when you perturb this stack. Cool. And as I said, how do you solve this system? You need to know this Newton's law and Hooke's law that tells you how springs work. And you get this kind of differential equation. So what's going on here? The left-hand side is mass times acceleration. Acceleration is the second derivative of position. And the right-hand side is this minus kappa x. So that's over here. So this is a differential equation. So you can solve it and you'll get, well, you won't get a unique solution. You'll get many solutions. So you need to know the initial conditions to fix down the solution. And once I know the position and velocity times 0, then you can determine xt and all t. And in fact, let's go through this. It's going to be pretty straightforward. And the way you do this is you take the previous equation, which was mx double dot equals minus kappa x, and you do this variable substitution, like omega is square root of kappa over m, which is well defined because these are positive numbers. And then you get this simple equation, which is x double dot equals minus omega squared x. You can see it has two solutions, sine and cosine. You can plug them in and see that both of them work. And so there's two solutions, and we had two initial conditions, and you can plug them in, and you'll get some solution like this. So x of t is this expression over here, and x dot t is this expression over here. So this is like a full solution to the system of one ball and one spring. Good. Okay. And so I've written this just so you know that there is a way to do this, but also I wanted to highlight something about the solution, which is that if we plot the position and velocity on the x and y axis, and we plot the location of this particle as a dot in this diagram, you'll see that this dot moves. And it moves not on a circle, but this is an elliptical path, an ellipse, which is a little annoying. We would like this to be on a circle. So one thing you can do is you can rescale the x and y coordinates, and then it'll look like a circle. And one way to rescale them is you multiply with the square root of the mass over here. You multiply with the square root of the spring constant over here. And the equation of a circle is that this coordinate squared plus that coordinate squared equals a constant. And I'm going to call that constant E, rather suggestively. So for those who are not physicists, do you recognize this equation? So this is the conservation of mechanical energy. So this is the kinetic energy, this is the potential energy, and they sum to some constant E, and this constant remains the same, even though the left-hand side of this equation are functions of time, the right-hand side is fixed, so the energy is conserved as the system evolves in time. Okay. I mentioned this because this is going to be relevant to the solution, the quantum algebra. Okay, so this was a full solution to how you work with one ball and one spring. You have n balls and n springs. It's kind of the same thing. It's just the equations look a little more complicated. And this is the second order differential equations that people were earlier asking questions about. So this is what happens. You have these n variables, x1 through xn, and you have n equations, one for each ball. And so the left-hand side is the mass times the acceleration of that ball. The right-hand side is the sum of all the forces acting on it. And so these are all the forces acting on it because of what it's coupling to other balls. The jth ball is coupled to the kth ball with the spring of spring constant kappa kj. And this is the force acting on it because of the spring I was talking about that's connected to a wall. And so you get this system of equations. It looks a little messy, but what you can do is there's n equations, and you can write all this into a matrix form. And what you'll get is something that looks nice like this now, where x vector is just a vector with all the x coordinates. This is the second derivative. M is a diagonal matrix, which is all the masses, just m1 through mn. And F is some matrix that just, you collect all these terms, and you'll get this matrix F. So you can write it nicely like this. So this is a second order differential equation in terms of these variables that are vectors of length n. And finally, again, if you remember in this system with one ball and one spring, we did this variable substitution to make the equation look a little prettier. And I'm going to do the same kind of variable substitution here. I'm going to define some variable y that is the square root of n times x. And then I'm going to take this guy and just change some variables. And that makes the equation look even nicer. It's just y double dot equals minus ay bar. And the important thing is a is positive semi-definite. And the reason I'm mentioning this is this looks exactly like the one variable solution we had earlier, which was like x double dot is minus omega squared x. And this minus omega squared is similar to minus a because a is a PSD matrix. So all of its eigenvalues are positive. So you really can think of it as the square of some number. So yeah, so this is the equation we finally care about. So if you don't care about all of this derivation, like this is the second order differential equation that we're going to try to solve on a quantum computer. And it comes about in this way, but if you just want to take one thing home, this is the thing we're going to use in the next few slides. Okay, so now there's enough setup that I can describe the quantum algorithm to you. But before I move on to that, any questions about this part? Okay, maybe everybody knew how balls and springs work except me, but that's fine. Hopefully this review helps someone. Okay, so what are we going to do? So as I alluded before, we already know that similarly in the time evolution of a quantum system isn't BQP. In fact, it's a famously BQP complete problem. And I want to map this problem to the time evolution of a quantum system. And okay, I just want to remind you of like the numbers that are involved here. So I want to think of a quantum system on log n bits, which is like, so originally if I had capital N masses in my ball and spring system, I have log n qubits, sorry. The vector space is of size n, right? So if I'm talking about log n qubits. But as we know for time evolution of quantum systems, if the Hamiltonian is sparse, the Hamiltonian governing time dynamics, we can actually solve this problem efficiently on a quantum computer, which is time poly log n, if n is the size of these vectors. And this is how the mapping is going to go. I'm going to take capital N, my original system, which had capital N balls, and map it to a quantum system. But the quantum system is only going to have log n qubits. So that's where the exponential savings is going to come about. That's where the exponential speed up is going to come about. Okay, so that's the big picture game plan. And like more precisely, what's happening is I'm going to take our problem, which is time evolution of n balls and springs, map it to the time evolution of quantum system. But the quantum system size is exponentially smaller. It's only using log n qubits. And when I say map, I mean like two different things. One is that I'm going to map the state of the classical system to a state of the quantum system. What that means is like a state of a classical system is positions and velocities. The state of a quantum system is the quantum state, the one that we all know and love. That's going to be on log n qubits. And note that this makes sense. Like I can encode capital N numbers in log n qubits. So, okay. And then I'm going to map these like how the system evolves. So there's just Newton's equations, like this equations I had on the previous slide, this second order differential equation, whatever, to the analogous thing for how a quantum system evolves, which is a Hamiltonian. And once I explain both of these maps and that these maps are consistent, then the algorithm will work. And so if you want to see this as a picture, what I just mean is that I have a classical state at time 0. I can map it to a quantum state at time 0. Classical state at time t, I can map it to a quantum state at time t. And if I evolve this with Newton's equations and I evolve this with Hamiltonian simulation, these two paths should be consistent. That's what I'm saying by maps. That makes sense. Okay, so let me tell you two ways of doing this. The first one is simpler, but has a bunch of downsides. But it'll be simpler to understand. At least the intuition will be clear of why you can map that equation to Hamiltonian simulation. So this is the first solution. So what was the equation we're trying to solve? So recall this was this y double dot equals minus a y vector, where the y vector was related to the x vector with some masses, and a was some PSD matrix that came about from your spring constants. So this is the equation I want to solve, but I want to map this to the Schrodinger equation, which is what governs time dynamics of a quantum system. So what does the Schrodinger equation look like? It looks like this. It looks like the derivative of the state vector is minus I times some Hamiltonian times the state vector. And this Hamiltonian has to be a Hermitian matrix. That's the constraint on it. So I want to massage this equation to make it look like this equation. That's the goal. That's what I mean by mapping the classical system to a quantum system. And there's actually, okay, there's one way to see this. It's kind of a trick. It may not make that much sense, but I'm just going to add the same term to both sides of this equation. The term I'm going to add is I square root a y. Let's just add this to both sides of the equation. And what you'll see is the right-hand side, maybe let's say the left-hand side. So the left-hand side should have two terms, which is the second derivative of y and I square root a y first derivative. And this guy over here, after this d by dt adds a dot on both of them, is exactly this term plus this term. And the right-hand side is also correct, unless I've done some algebra error. The I square root a y dot is the first term here, and the second term is coming from this guy, because I took square root a out common, and I square root a out common. So, and why did I do this? Because now it looks like d by dt of something is I times a Hamiltonian times the same thing, which looks exactly like this equation over here. So this is just like syntactic manipulation of this second order differential equation to make it look like a Schrodinger equation. But you can actually carry this through, and this gives you a quantum algorithm. It's just not it's not as good as the one I'm going to talk about later. But I thought I'll show this. It kind of gives you some idea for why it's even possible to do this. Maybe it gives people some intuition. Yeah, Mars.
Normalization.
Sorry, normalization of what?
Like this side is unit vector, and like here, the shift.
Yes, that's a good question. So you're saying like this guy, but this is so this is firstly Hermitian. So that's because this guy here was PSD, so the square root is that's fine. So this will actually be a norm preserving map, because if you start out with a Hermitian in this Hamilton's equation, this Schrodinger's equation, the time evolution will be this unitary e to the IHT, and that's unitary, and so this guy's norm will actually be conserved. It's not clear to see why the norm will be conserved. That's right. Yeah, when you define a quantum state, you can define the quantum state. That's the normalized version of this, and its norm will actually remain preserved. So that's not a concern. But this way of looking at it is like not very intuitive to me. So I'll present a second way that makes much more sense. But this might help some people. So I'll explain this solution as well.
Sorry.
Yeah.
This is a silly question, but why don't you just take the second derivative of the Schrodinger equation?
And so that one looks like this, right? That will have one extra dot on this side. So we have two derivatives here, but we'll have one derivative here. But here's like the second derivative related to the original thing without. So
Okay. Well, you can, but maybe okay.
or maybe, okay. Maybe we'll keep them like that. Okay, so let me tell you the better solution, which is the one that we use, which gives you more efficient quantum algorithms. Which is, so recall, what are we trying to do? Right? We're trying to map the classical state at a given time to a quantum state. So we're trying to map these two n numbers, these positions and velocities, to a quantum state. So yeah, as Maris pointed out, like quantum states have norm 1, right? So we need some mapping that takes these numbers, maps it to a vector whose norm is 1. And in fact, we want the mapping to be such that the norm remains norm 1 throughout the computation, right? Because a quantum time evolution is going to preserve the norm of the state. So I want some quantity that's related to these parameters that is actually conserved throughout the time evolution. And we talked about this earlier. This is like one example of such a quantity that's conserved throughout time evolution is the total energy. So which is like, this would be the conservation of energy equation for n balls and n springs, which is like, this is all the kinetic energies, this is all the potential energies for the pairwise springs, this is all the potential energies for the springs with the balls and walls. So this is a conserved quantity. So once I have some equation like this, which is like a bunch of things, left-hand side, these are all time-dependent things, but they are conserved with time, I can define a quantum state whose entries are essentially these guys. And the quantum state's norm will remain the same, or it'll remain E, but I'll divide by 1 over square root E or something outside so that the norm will remain 1 throughout the computation. And so what I'm going to do is I'm going to take a quantum state so there's entries of 3 types. There'll be a bunch of entries that look like square root of a mass times a velocity. There'll be entries like this, and like I'll tell you how many of each type there are. There's like n masses. There's like n choose 2 of these pairwise springs, and then there's n of these springs to walls components. This guy just turns out to be the vector y bar I defined earlier, because when I was doing this variable transformation, I transformed the x variables to y variables by multiplying by square roots of the masses for some mathematical convenience, but it turns out to be nice. This is just the y vector, y dot vector, sorry. And this is some linear combination of the y's, because it's some linear combination of the x's, but x's are related to y's through some linear combination, so it's, again, some linear combination of y's. So if I show you the whole vector, it's going to look a little ugly, but this is what the vector is going to be.
Is it clear that you calculate this order n vectors, entities in the vector? I mean, the naive thing would be to introduce an auxiliary variable and make a first order differential equation. I do not normalize, so which seems to be somewhat maybe slightly non-trivial point. So my question is indeed, is it clear that order n squared terms is optimal to keep the normalization, or could there be an order n construction?
Oh, I see. Can you do it with fewer? Right. So,
Well, I mean, if you just want the first order equation, you can do it with 2n terms. Right?
right.
I mean, that's what you always do, no? You
That's right.
so call it y dot and the new variable z, and then it's a first order differential equation. But of course, it's not non-preserving, because you maybe there's a trick to make that one non-preserving.
So the previous solution that I gave actually uses exactly a vector of length n, right? Which is this guy is actually a vector of length n, and I'm using the imaginary part to put in like the position stuff and the real parts during the velocity part. So this is really the most succinct way of doing it. I mean, you certainly can't do better than this, and this achieves it. But it's not as intuitive as.
Take the real problem and map it to a complex problem, basically.
Take this right away.
So basically, you take the real second order equation and map it to a complex first order
Right.
equation.
That's one way of thinking of this solution, right? I used the real and complex imaginary parts to store both the vectors I want to store.
So here you could extract stuff from that. It's not so obvious how you would extract real imaginary parts.
How do you extract stuff from it? This is why. Yeah, this is why the solution is not that great, because now I'm combining the real and imaginary parts, and like it's going to be harder to extract the quantities I care about. In the second solution, like all the quantities I care about, like kinetic and potential energies, appear like by themselves. It's going to be nice for computational problems like that.
There's no intermediate thing. I mean, with 2n amplitudes, you would have access to everything immediately, and you would still not scale perfectly in n, right?
That's right. I don't know.
Which again would be the naive way, I think, how you would learn in an ordinary differential equation course.
And you'd want that to be norm-preserving, right? And
Yeah, exactly. That's not obvious. That's why I'm asking if there's a way.
I don't know.
Whether there's some argument why that shouldn't be possible.
Yeah, I don't know. Yeah. Any other questions about this part? Anything else so far? Or was I? Oh yeah, something about this state that we're going to talk about. The important thing about the state is its norm is 1. And the norm 1 equation is exactly the conservation of energy statement. So I'm storing, essentially what I'm storing is I'm storing the kinetic energy of the first ball in the first component, or a square root of the kinetic energy. The first component, the kinetic energy of the second guy, and the second component, and so on. And then here I'm storing the potential energy that's stored in the spring that connects ball 1 to ball 2. So each component of my vector has an interpretation. It's storing some kind of energy, either kinetic or potential.
What is K11, for example?
So that's the spring that connects the first ball to the wall.
Okay. Yeah.
So this is storing the energy stored in that spring, and so on till the last spring. And this is like the super explicit way of writing it down. This is like the more compact way of writing it down. It's this y vector, which was same as the x vector up to some change of multiplied by this mass. And this second part of the vector is again some linear transformation on these position coordinates, which I will represent by b.
Compute the matrix square root, right?
Yes, I'm going to come to that.
Obvious.
In the previous solution, you mean?
Yeah, in the previous slide, they had a square root of a.
Here?
Yeah.
Yeah. So this is part of this solution has downsides because you only have oracle access to A in the assumption or whatever you're going to circuit. So you can do Hamiltonian summation with the square root of a Hamiltonian that you have access to, but like this will require, essentially phase estimation and stuff. So you're going to have pretty bad dependence on the error. You have to resolve stuff. It's not the most efficient way to do it, but you can do it. We give this solution in our paper as well. Like we work it out. We tell you exactly what the overall complexity is going to be. It's going to be much worse than the second solution, but
I see.
but it works.
The second one has nothing to do with this first
No, this is kind of just inspiration, or like this is one way to solve the problem. It's totally a valid way to solve the problem. It's just not the best way to solve it. Like the second solution is going to be better. So I presented just so that it's clear at least that in principle you can solve it, because this is how you can in principle map this equation to a Schrodinger equation. But I'm going to use a different mapping in my second solution, which is to have these states that look like this, which are normalized because of the conservation of energy. in the previous case, it was not clear why that state was norm 1 even, right? It was just like some real part plus complex part. I added them. They turned, it remains, the norm remains conserved, but that was not totally obvious. Here it's clearer to see because it's just like, well, this is this, this is the total energy that remains conserved throughout the computation. And yeah, once you have chosen this representation for our system, like that, I'm going to map a classical state to this vector, it's going to be much easier to see what the dynamics looks like.
Sorry, which
Yeah.
one is the y dot and the differences belong to which part?
To the y. So y and x are basically the same thing. So if the masses are all 1, then they are literally the same thing. So you can just think of x and y as the same variable. So these are the dot variables, the first n. And these are like linear combinations of non-dotted variables. So that's why it's some linear transformation. Yeah. So yeah, if you want to just think of x and y as the same thing. And right, so now I have to show you what is the Hamiltonian. So as I said before, this is the state we're going to talk about, y dot b dagger y. Its norm is 1, independent of time. That's good. That's a good start. The second fact, which is true, but I won't prove it here, is that, in fact, bb dagger is a. This is the a from, we're trying to solve y double dot equals minus ay. And this happens because, essentially, a is a graphical Gaussian, and b is its incidence matrix. It's just a thing that is true. You can verify it by computation. And that's really nice because, yes, as I was saying, a is this is the equation we're trying to solve. Like the second derivative of y is minus a times y itself. And what you can do is you can just write down this equation and see that any solution y actually satisfies this. So this is a matrix equation. We can write down the two separate equations that it's talking about. The first equation will give you essentially y double dot is minus ay. Second equation is kind of trivial. And this has, again, the format that we like, which is the Schrodinger equation format. It's saying that the time derivative of some vector, now it's normalized, it's norm 1, which is cool, is minus I times some Hamiltonian times the same vector again. So this is the Schrodinger equation, and we can solve this with Hamiltonian simulation if you can create the starting state. So if you can create the state corresponding to psi 0 on your quantum computer in polynomial time, then you can create psi t by just appealing to known results on Hamiltonian simulation. And recall what I said earlier, like the constraint I'd put was that you only have polynomial many non-zero entries. And yeah, it's a known fact that you can create quantum states with polynomial many non-zero entries on a quantum computer. So it's okay. So we can create the initial state. We can do Hamiltonian simulation. You have to check some conditions for Hamiltonian simulation to be true. Like the matrix has to be sparse and it has to have like bounded entries and so on. But it'll work out with the assumptions that I gave. And so you'll create the state, just call a off-the-shelf black box Hamiltonian simulation algorithm, and get this state, or rather you get the final state, which is the same thing, but at time t. And once you have the state, you can do many things with it. One thing you can do is you can sample from the corresponding probability distribution. This might tell you something interesting. So it's sampling from this distribution where, like, let's say you fix the total energy to be 1. So it's sampling either a ball or a spring proportional to the amount of energy that's stored in it. So that might be a useful task. But another thing you can do is you can estimate some quantities that you care about. Like, for example, you can estimate the first entry to inverse polynomial error. Like the first entry, along with the normalization to inverse polynomial error. This is just like, if I give you a probability distribution and I tell you to estimate the first entry to, additive error epsilon, you need like 1 over epsilon squared copies of the probability distribution. So same phenomenon. So I can get you the kinetic energy of the first ball divided by E, so the fraction of the total energy that's stored in the first ball to some inverse polynomial error. Or the potential energy in some spring, or the kinetic energy of some subset of balls, or like, you can make no problems. Is the total energy. It's like this normalization constant here. So that's right, but when you started, you only had polynomial many of them moving, so E is some polynomial in average number. And you can actually compute it before computation starts, right? Because the initial position and velocity vector was very sparse, so there's only polynomial in many positions velocity, so you can just like go through them, compute E. It's going to be some number between 2 poly n. So
for the typical ball,
the energy stored in a typical ball might be extremely small. That's right. That's why I can only give you additive poly n estimates. So like typically the energy might be much smaller than poly n, then you have nothing. Except what we show is the BQP complete problem is one where you just have to report this entry to additive 1 over poly n, and that already captures this.
So by BQP complete, what is your decision?
It was a decision problem that I stated a while ago, which was just whether the first entry here is bigger or smaller than, so I'll give you 2 numbers, A and B, and the inverse polynomial is separated, and you can tell me if this first number is less than A or bigger than B.
if I can solve the classical dynamics of that velocity, can I solve this problem?
Yeah, definitely. Because it's just asking, is the first ball, does it have kinetic energy more than something or less than something?
Then I must ask you the following. What are you relying on in terms of these generic results from Hamiltonian simulation? Because something to me seems to be contradictory. If you're telling me I can make this stochastic system, simulate this Laplacian classically, then it will solve your quantum thing. But I agree that your mapping is working in one direction, but I'm not seeing how this is,
The classical algorithm will take exponentially longer because you'll write down this n by n matrix, you'll diagonalize it, do linear algebra, and so on. So it'll take, yes, it'll be an exponential time algorithm compared to this being a polynomial time algorithm. So that's the difference.
Okay, that would make sense.
Any other questions?
So basically, the conservation of energy is the conservation of norm.
In this way of thinking, yeah. That's right.
And what's the advantage of doing this solution?
So in the simple one, firstly, you don't have access to these quantities directly. So we had in the simple solution, there's the real and imaginary parts were coupled, which is not a big deal. But the thing is that we don't have these terms that correspond to separate string constants. That's one thing. Maybe the more computationally annoying thing is you need to square root A Hamiltonian, which you just don't have access to. You only have Oracle access to the entries of A. So now you have to do Hamiltonian simulation with the square root of the Hamiltonian. So that's going to add overheads of.
And how come you got rid of this thing?
We just use a completely different mapping. Right? So this was like the initial mapping, but like this solution is abandoned when I go to the next slide. So this is a totally different way of thinking about how I'm going to do the mapping. If you're wondering like conceptually how we're getting around, like you have access to Hamiltonian, but we want to do Hamiltonian with summation with square root. How do you get around the fact that you would in general need to do phase estimation? It's because the Hamiltonian is special. It's the sum of PSD terms, and this is you can do in general for Hamiltonians. That you could, if you have a Hamiltonian that's the sum of, what's this technique called? I think it's called spectral gap amplification. I think like Rolando Soma is one of the authors of this paper, and it's like if you have Hamiltonian that happens to be the sum of projectors, and you have this explicit representation written down. It's not an oracle type thing, just like you have this written down. Then you can do something much better, which is that you can. Essentially you can amplify the spectral gap. So if you're trying to look for the ground state energy, you can do quadratically better than what you would have thought you could do. So it's the same trick underlying this representation as well. Yeah. Any other questions?
So if I take some Hamiltonian, can we map it to this problem then?
Right. Let me tell you about that part. So that's the completeness part, the fact that this problem actually captures all of quantum computing. And so let me get to that.
Can I ask a question? So now the form factor is very, very long, but the output seems to be only like the to output the information of regarding one coordinate. How do you do that?
How do I get this? So so for example, like in the way I formalize the problem, which is also this thing, the general problem. In the special case, I said all you need to do is figure out this entry to additive one-over Pauli error. And that's just this fact that if I allow you to sample from a probability distribution and I ask you what is the first entry of a probability distribution, like what's the probability that you sample 1, you can estimate this probability to additive epsilon, 1 epsilon squared samples. So this quantum state, like once I measure in the standard basis, you'll get this entry with probability that is the kinetic energy of the first pulse. And I just do this enough times, see how many times I get that, and that's going to give me an estimate of this number. And the decision problem was just to decide if this number is bigger or smaller than some number that's part of the
Question is, how many times do you sample? Isn't this pass some polynomial?
That's right. So to get, so if I want the quantity to 1 over Pauli n error, I'll have to sample it like this polynomial squared number of times. That's still a polynomial. Okay, good. So I'm also running out of time. But so let me give you some intuition for why it's also this captures the power of quantum computing. But to prove BQP completeness, what I would do is like go through the circuit to Hamiltonian reduction, starting from an arbitrary quantum circuit and showing how you get a system of all the springs. So this reduction is kind of painful and maybe not super illuminating. Instead, let me give you a different kind of evidence for why this problem is hard, which is that you can use it to solve the glued trees problem, which is a famous problem that has an exponential separation between quantum and classical query complexity. And if you've seen this before, maybe you might enjoy this because it's a natural algorithm for this glued trees question. So look, let me tell you a little bit about this. So some of you have probably seen this before, but let me describe this again anyway. So the glue trees problem is an oracular problem. So you have access to a black box that's encoding some graph that looks like this. And what's going on in this graph is you have some entrance vertex here. You have a balanced binary tree going out from this with n layers. And the same thing here. There's a balanced binary tree going out n layers. And in the middle, there's a random cycle that connects these. And the oracle you have, and you know the name of the entrance vertex. So that's what you're given. And the oracle you have, you can give it the name of a vertex, and the oracle will tell you its neighbors. So for example, if you tell it the entrance vertex, it'll give you the labels of this guy and this guy. If you give it this vertex here, it'll give you the labels of this, the forward two guys, and this guy as well. And you only have this kind of oracular information. You're given the label of the entrance vertex, and your goal is to output the label of the exit vertex. This is the glue trees problem. And this little n is the depth of both of these trees. So the total number of vertices here is something like 2 to the n, or 2 times 2 to the n, or, whatever. It's exponential in little n. And what's also known is that any classical algorithm, whether it's classical, deterministic, or randomized, needs exponentially many queries, exponential in n, to solve this problem. Whereas there's a quantum algorithm, which is based on a continuous time quantum walk that solves this problem with polynomially many queries. And I'm going to show you how to reproduce the quantum algorithm using balls and springs in kind of the most obvious way, which is I'm going to put a ball at every vertex, and I'm going to put a spring at every edge. So that's kind of what you would do with a problem like this. So so the red dots are balls, the blue lines are springs. All the balls have mass 1, all the springs have spring constant 1. So it's a very simple system in that sense. And what I'm going to do is I'm going to start by perturbing this entrance vertex. This is the only vertex whose label I know, right? So, and the theorem that we show is that there is some time, t, which is polynomial, at which the entrance vertex will always also have inverse polynomial velocity. So what's happening is I give the entrance vertex some velocity, and that this like energy propagates to the system, and all the balls start moving and whatever. But there'll be some time t at which this guy will have inverse polynomial velocity. This is not obvious because there's exponentially many balls here. So this is something that you have to prove. But once you've proved this, then because of the thing we show, you can learn the name of the exit vertex. So in this glue trees problem, I forgot to mention this, but once you have a candidate for the exit vertex, you can always check it because it's the only other vertex in the graph that has two neighbors. So even if you run our previous sampling algorithm, it gives you a couple of candidates. That's okay. You'll just check them all with the oracle. So you can think of this as a different way of rederiving the glue trees algorithm that has nothing to do with quantum walks. Or of course, there's a quantum algorithm involved, but at least if you wanted to explain this algorithm to someone, you could just say, oh, it's just a bunch of balls connected by springs, and I perturb the first guy, and after polynomial time, the last guy will pick up some kinetic energy.
Is there a physics intuition why it works?
Good question.
Nice picture of springs.
Yeah, is there a physics intuition for why it works? So there is a physics intuition for why this works, which is actually the same intuition for why the continuous time quantum walk works, which is there's actually you can reduce this to a smaller system of just 2n balls and springs, which corresponds to the columns. And this perturbation will transmit through the columns equally. Like, so all the balls in a given column behave the same way. And so the reduced system is just a bunch of 2n balls connected by springs of the same spring constant, except in the middle there's a different spring constant. And then you just analyze this classical system, which is now of size n. So that's something you can even code up on a computer or whatever, because you have polynomial time. You analyze it and figure out at what time will I actually propagate some velocity to the last guy. And yeah, it works. And there's a point.
Here the springs have different weights in the middle or no?
No. So all the springs here appearing here have spring constant 1.
This funny observation is that when you do this with the springs, it would also not know what the path is.
Right. It doesn't help you find the path. Right. Yeah, this is a famous open problem with glue trees, right? Like finding a path between the entrance and the exit. And yeah, our solution doesn't help you do that at all.
So what in the glue trees problem is what's essential for different weights in the middle, square root 2 or something?
No. So what happens is when you analyze this in the subspace of these column registers, you write down a separate 2n dimensional system. Then it turned out that the middle guy had weight root 2, but the other ones had weight 1. But that's just an effective system that you remember. The original system has all equal weights. Yeah, because you don't want to leak any information to the algorithm about which are the middle edges and which are the side edges. So all the edges have the same weight. And that persists in our formulation as well. All the springs have the same spring constant. And so our algorithm solves this glue trees problem. And as a corollary, because the glue trees problem reduces to our problem, as a corollary, any classical algorithm that simulates our algorithm, in fact, will also be able to solve glue trees, which also needs 2 to the omega n queries. Like the classical lower bound essentially goes through for our problem as well as a corollary of this result.
Can you make more specific the mapping between the Hamiltonian and the velocities in the problem? So basically, given any Hamiltonian on any graph, you can just map it with balls and strings, and then the map would be what's the map from the state to the velocity?
So you're saying given, so this is like the BQP completeness part. You're saying like given any quantum Hamiltonian, how do I map it to a system of balls and springs so that the dynamics of the...
Yeah, for the second part, you're saying, take, for example, Chance construction, but any Hamiltonian, and place balls on the vertices.
no, this is not a general construction. Like this only works for this glue trees problem.
Why? So what's the statement here exactly?
So here, just I mean, the only thing I want to present in this talk is that we can solve the glue trees problem, which is like...
But why does it work? Does that come from a general statement connecting the Hamiltonian?
No, it doesn't. We have to do a different analysis too. I mean, the analysis at the end of the day is the same thing. That in the glue trees problem, what you do is instead of working the space of two to the n things, you work in the space of 2n things. We do the same thing, but what we need to prove about it is slightly different because the dynamics is different. It's balls and strings. It's not a quantum walk propagating.
So there's no such general.
No, our BQB completeness reduction will tell you that you can take any circuit and map it to a balls and spring system, but we don't show how to go from a arbitrary Hamiltonian to a ball. But I suppose you can in principle.
Can you say more about why this map works in this case? What makes it?
In this case?
Yeah.
Right. So the analysis is similar to the analysis of the glue tree problem, which is okay. We work in the space of you have this reduces to a system of just 2n balls, one for every column here, and the spring constants will turn out to be they'll all be the same except the one in the middle will be like √2 times bigger or something. And now you have a classical system of 2n things, and you have to analyze the question of if I perturb the first guy, if I give the first guy velocity 1, will there be a time, this is polynomial, at which the last guy gets velocity 1? One thing you can do is you can just solve this on a computer or something, and you'll see that it works. But the way we prove it analytically is we say, we write down this classical system of equations. It's a matrix. As I said before, if you want to solve a system of balls and springs, you can just write down this second order differential equation. This y double dot is minus a y bar. We take that matrix, we analyze its spectrum, and we show that this entrance state has inverse polynomial overlap with all of the eigenvectors. So
isn't it the same proof as in the
yeah. It's the same proof, except we have to. I mean, it's the same idea exactly, but we're proving something slightly different. Right? We're not showing that the quantum walk propagates. We're showing that this physical disturbance of velocity goes through. So it's a slightly different equation, but the proof technique is exactly the same. You analyze the same thing. You show something about the eigenvectors. You show it has good overlap. You show that property.
Yeah, I'm just wondering why it doesn't generalize to every Hamiltonian.
It feels a bit related, no? If you go to a quantum limit where, I mean, you could think of it as quantum mechanical harmonic oscillators, right? If you put a strong enough coherent state in there, it's a classical system, right? And if you put a single excitation, it should be basically a random walk, I think, right? Imagine you have this chain of bosonic oscillators, you put a single boson, like you put a slide, this excitation you can imagine on the left node, it should basically be a random walk. There's a single excitation in that system which moves around. I'm not sure if it's exactly the same random walk because I'm not exactly familiar with the details. It could be the same random walk, so it could be like two extreme limits of the same system, right? One mechanical harmonic oscillator system, and either
But
the
you're
single
thinking of it like
excitation
a
or
random
a
walk.
large number.
It'll take n squared time maybe to go from 1 to n, whereas the quantum walk moved in linear time. Quantum walks propagate faster than random walks, right? Quadratically faster. So you're saying the classical system, if we solve it, it'll be more analogous to a random walk than a...
No, I'm saying, I mean, you could think of both things, it feels to me, I'm not sure if it's exactly the same random walk, as a system of quantum mechanical harmonic oscillators, where in one extreme case you put a very strong coherent state, which means basically they behave classically, I think. And in the other case, you put only a single excitation, which means it behaves like a random walk, really, right? Because there's only a single excitation, which will hop around in one way or the other. It's exactly the same random walk, but it's a quantum random walk, right? So it could be two extreme limits of the same situation. I mean, quantum mechanical harmonic oscillators have a classical limit, and I think that one is really well understood.
That could be true. Yeah, I have no idea. But maybe actually coming back to Dory's question, like I think there's probably something general we can show, but we didn't show anything of the sort. I guess what you would like is some result that says that you have a quantum Hamiltonian, you map it to a classical system of balls and springs such that the time evolution of the classical system recovers somehow the task that was solved by the original quantum Hamiltonian. Yeah, it's probably something that we should show.
Can you reduce from the Charles et al. BQP completeness of random walks?
Yeah, that's what I'm asking.
Instead of from circles?
Yeah, that should probably work. So this is the this is the completeness of which quantum walks? Which paper?
Exactly, just take the quantum walk. So what challenge is to prove universality of quantum walks, basically construct given a circuit, you construct an exponential size block, which basically duplicates the geometry of the circuit. So it's like throwing the circuit on a 2 to the n size grid in 2D, and then it's just a quantum walk on that with the Hamiltonian having just weights 1 on each edge. And then again, it's explicitly like what you were doing, etc. So if you could start starting from Charles' result, then and you'd have a general statement that says that from such a quantum walk you can just place balls on the nodes and strings on the edges, then BQP completeness would follow.
Yeah, that sounds right. I mean, that should be possible. I didn't think about this before.
Sorry?
So yeah, maybe I should. Yeah. Okay. So this was the.
Okay, this probably.
Oh, somebody's done that. Oh, okay. Oh, I see. Okay, maybe. Okay.
Sorry,
Tell me more about it.
just a quick question about this. So this may be maybe output on this, or I'm just wondering what happens in this blue trees if the middle layer has a short description. What fragment of BQT is that? It's a short description. So if you guarantee that it has a short description and it's very regular, is that classical, or is it a nice is it an interesting fragment of BQP?
So this problem is, I mean, it's a purely oracular problem. It's not BQP complete because it doesn't have a succinct description. So it's only like you can treat it as a query complexity problem, which has an exponential gap in query complexity, but it's not. Yeah. This blue trees is not BQP complete. But yeah, you're saying if we just somehow put some constraint on this being simple, yeah, I don't know. Maybe it depends on in what way it's simple, and if the classical algorithm could somehow learn that.
No, it's not going to.
So this is not related to BQP.
So the next slide is say summary to show BQP completeness. So we had the distance.
Right. Oh no, I didn't get the BQP completeness because I thought that would be this would be more fun to
That
see.
was the most interesting part.
You want to see BQP? Okay.
That was his thought.
Yeah, you just do a circuit to Hamilton reduction. Okay, no, it's not just that, but yeah. I mean, essentially, you take our forward reduction and work backwards through all the steps. Some of the steps don't go backwards because what will happen is you'll reach a Hamiltonian that doesn't have all positive entries and so on that we need for spring constants. But it's maybe it's the same trick that's in this Charles et al. Paper that allows your Hamiltonian to all have entries one. You embed this.
It's just printing with a structure of the matrix. You get until it has enough properties.
Yeah, I guess that's one way to think about it. We just, there's a couple of things we need to fix. One of them is all the entries don't have the same sign, but you fix this by enlarging the space and like working with like one of the registers being kept minus or something, so that like secretly there are minus signs in the Hamiltonian, but like not in the standard basis. It's also the same thing that's on this quantum walk paper, I think. If I'm thinking of the same quantum walk paper, is this the one that says the Bose-Hilbert model is clearly complete?
No, it's
it's an
universal. The quantum walks are universal.
Oh,
I think it does follow because it basically is like electrical networks. The argument there.
Oh.
It's this
Okay.
single walkover paper, right? Not the
Yeah.
multiple.
Okay, yeah, I should look at that. Okay, yeah, but I guess I'm quite out of time. So let me just end with open questions. I guess that's two obvious open questions. Can you do something with our algorithm? And can you do something with the completeness reduction? I guess the algorithmic question is like, can you use this to solve interesting problems that people actually care about that are natively about either balls and springs or whatever, or coupled harmonic oscillators in general? The other way around is like, can you design new quantum algorithms using the intuition from just balls and springs, like we did for this glue trees? And there are some quantum algorithms we can recover, like Grover and like this NAND tree problem and the glue trees as I showed previously. And like, yeah, maybe most continuous time quantum locks I think can be recovered, but maybe what Dory was saying now, I think maybe we just prove some kind of general theorem just says that if you have a Hamiltonian, so it might not just be like special cases like this, but there might be just something general that can be shown. We can recover all of these algorithms. But it'd be cool to like come up with a new quantum algorithm by reasoning about classical systems, because there's a lot of people who have more intuition about classical systems than they do about quantum systems and quantum algorithms. And so now maybe somebody from that background comes and develops a new quantum algorithm using this connection. That would be very cool. Yeah, these are some open questions. And yeah, that's all I wanted to say. Thanks everyone for staying.
So is this limited to classical harmonic oscillators? Will the same result basically also apply if you have quantum mechanical harmonic oscillators? I mean, my everything is quite acting including the initial states. Because kind of the math is very similar when you look at Gaussian bosonic systems and classical systems, right?
I don't know the answer to that.
Because then, if that would be the case, this would probably form a link towards the random walks, right? Because the random walks is kind of just a case where you put basically zero excitations, and then the subleading terms are single excitation. So that could maybe make a connection with that.
Yeah, we can talk about it. But I don't know the answer to that, and because I also didn't know what a classical harmonic oscillator was until I started this project 6 months ago. So this is all new to me. So like, I don't know what a quantum harmonic oscillator is. Right, yeah. But I haven't thought about this question just for this reason.
Your simulation, you get you need time t to simulate these springs for time t, or you get some quadratic speed up?
No, we need time t to simulate for time t.
You can't like pass it over.
No, I mean certainly not the way we do it. I'm wondering if we can also prove that you can't fast forward. I don't know. Yeah, I'd have to look at the BPP proof to see if it like takes a circuit of certain length and maps it to it. But at least our algorithms go linear in T.
You know, like all these algorithms that are like, you have electric network, you want to know what's the, resistance or something. Like they're quantum algorithms. I mean, I guess this probably relates to what you say, these continuous time quantum volts. But they somehow fit in your philosophy and framework. Basically, could you say that like these on-the-walk algorithms that are using this electrical network formalism, that they are essentially it's an instance of using these golden springs with Calvinist mode?
Yeah, that's a very good question. I don't know. Yeah, I'll have to look at those electrical networks based algorithms.
I think another interesting thing is that, for example, you could ask the reverse question, like, if you have when you showed this group trees, like if you want to simulate a quantum algorithm with a classical physical system like balls, like the unitary evolution, you could simulate it by you kind of you pulled one of these balls and then the rest of the balls started bouncing and their velocities and coordinates and the amplitude in the circuit. But then you could ask, how would you simulate the measurements with the ball system? Because then what you would want is to sort of after the measurements, you have all the particles are fixed and only one of them is bouncing. Sort of like all the energy sort of is transferred to that one. I don't know if there's like a physical mechanism that would sort of, with probabilities proportional to the volumes, the velocities and the coordinates, sort of select one of the balls and the rest is
Simulate the measurements.
yeah, because because like, you could ask the reverse question, which is very classical, in like quantum computer. And then another remark is that there is, from a couple of years ago, there was a paper about correspondence between Grover's algorithm and this kind of mechanical system where you have like a wall, you have these two blocks that can slide and goes onto one. And basically, there's like one block that's standing, another block is coming, and then it starts sort of like bouncing.
Right.
And there's a really, like, you can look at the conservation of energy of these two blocks. And, it's kind of like conservatively coupled, what the norm of the concept. And these two bounces, like between the two blocks and between the wall, they corresponded to reflections in Grover's algorithm. There was a really nice correspondence between this two sort of mechanical system in Grover's algorithm. And I mean, basically, it seems like there should be indeed like kind of more potential for basically having some, I don't know, like, mappings between mechanical systems.
Yeah, that sounds very plausible. In fact, Grover, I think himself wrote a paper on how you can think of Grover's algorithm as something with coupled pendulums. And coupled pendulums are the same equations as balls and springs. But what you're talking about, I think, is a different thing. But
Yeah, no, that was very recent. There's like a video about
I saw a video of this.
Yeah, exactly. Yeah.
Right.
So after this video, like somebody wrote this paper. And it's really elegant. It's very short and it just explains.
It might be, yeah. I think if you look at it the right way, especially if like energy is involved, like it might be just doing this. Yeah, I mean, I agree. There's like many interesting directions to go from.
If you let the balls collide and impart momentum to one another, do you think you could simulate that quantumly?
I don't know. No, I don't know. Like, I don't know any other classical system for which this works. Like, just coupled harmonic oscillators. Like I don't know how to make this work for balls interacting under gravity or something like this. It's somehow special to this.
I think an obvious next generalization is to take relativistic effects into you have these exponentially many balls, and presumably some of them can start moving really fast.
You really need that to someone with more physics experience than me.
I mean, more seriously, there are like in physics, there's like a Klein-Gordon equation, or there's like all kinds of differential equations that are very fundamental, that are kind of more complicated, and presumably you can also simulate them.
There is a lot of work on like solving differential equations on quantum computers already. Yeah, I don't know if it covers the specific equations you care about, but yeah, there's certainly a lot of work. This one in particular had not been considered before, but yeah, there is a whole area of like looking at differential equations, solvers, and sometimes it works well, sometimes it doesn't.
Yeah.